Let's go ahead and prove the quotient rule for derivatives. So the claim is that if h of x is equal to f of x divided by g of x, okay, of course we're assuming that h is smooth and continuous, which means f and g must be smooth and continuous. And of course we're assuming g is never equal to 0. Okay, h prime of x, according to the claim, is the following. F prime of x times g of x minus f of x times g prime of x, okay, all divided by the square of g of x. Okay, let's prove this. And we just finished with our proof for the product rule for derivatives. So as I'm brainstorming right now, I'm thinking probably we're going to be using the same techniques, or many of the same techniques, I guess. Okay, so by definition, again, using the definition of the limit of a derivative, or the definition of the derivative as a limit, I should say, h prime is equal to, okay, so we get the limit, and since we've chosen h, we're going to go with k goes to 0. Okay, so it's going to be h of x plus k minus h of x all over k. Okay, very good. This is going to be equal to the limit as k goes to 0. Okay, so we're going to have f of x plus k over g of x plus k, okay, minus f of x over g of x, and then all of this divided by k, which is the same as multiplying by 1 over k. All right. Well, clearly we're going to want to find a common denominator here. So let's do that first. I don't think that's going to be enough, but that is certainly going to be something we're going to want to do initially. So it's going to give us the limit as k goes to 0. Okay, multiplying top and bottom of this fraction by g, multiplying top and bottom of this fraction by g of x plus k. We're going to get the following. Okay. Okay. Okay, just put a k down there as well. All right. So that's what we have. Now, clearly, this is not going to be enough. We're going to have to do a little bit more than this. So let's think about what we did for the product rule proof. What we did is we added something and then immediately subtracted it back off. Okay. And we have to think strategically about what it is we're going to be adding and then immediately subtracting back off. We want to have an f prime in our final statement, and we want a g prime. Okay, so notice we get an f of x plus k here to the left of the minus sign, and here we get a g of x plus k. So if I subtract an f of x, g of x, and then add it right back on, at least for this first part, as you can see, I'll be able to factor out a g of x and then have that f of x plus k minus f of x, which of course is the numerator portion of the derivative. So let's try that. Okay, if you didn't catch that, it's okay. Just watch what I do. So we got the limit as k is trending to 0. And then we've got here f of x plus k times g of x. Okay, everything stays the same for now. Okay. And now, just in the numerator part, we're going to subtract off f of x, g of x, and we're going to add it right back on. Okay? Not affecting the equivalence. Still just as equivalent now as it was before. Okay, this is just like adding 0. That's all you're doing. If there's a hidden complexity that's revealed, okay, when you do something like this. I don't mean complexity in the sense of complex numbers. I mean in the regular colloquial sense. When you impose a sense of complexity, you discover things that you probably would not have noticed. Now notice what I can do. The first and third terms have a g of x in common. I'm going to go ahead and factor it out. Okay, if after taking g of x out of the first and third terms, what I have left here is the following. Okay, notice how I'm just taking care of the numerator separately from the denominator. Okay, it's a strategy that is super helpful. Okay, now second and fourth terms. What do we have in common there? Well, we have an f of x in common. Better yet, we got a negative f of x in common. Okay, let's take a negative f of x out. And we wanted a difference anyway, didn't we? Yeah, so it's a good thing we have this difference here. Okay, so taking an f of x out of the second and fourth terms of the numerator of this portion, we have left g of x plus k, okay, minus g of x, just like we hoped. Just like we hoped. Okay, see those derivatives already waiting for us here. Okay, so g of x plus k, and then of course k. I guess we should put braces here or something like that. Let's go ahead and zoom out one step, maybe two. No, just one. That's too far. We don't have to go out that far. Okay. All right. Now, we know that the limit of a difference is the same thing as the difference of limits, and we know that the limit of a product is the same thing as the product of limits. Okay, so we're going to just be creative and set this up in a way that, well, that helps us, to be frank. Okay, so here we go. We've got g of x, because it doesn't even depend on the limit, actually. There's no k in here. So we've got g of x, and then we've got here now the limit as k trends to 0 of f of x plus k minus f of x, k over k. All right, I'm just going to apply this k here. We're going to use the following principle: a plus b over c equals a over c plus b over c. Okay, this property right here. Okay, that's what we're doing. Okay, these still have to divide into this term. I've only dealt with the first. Okay, they still divide in here. So let's go ahead and do all that. Minus. Now, again, the limit's not concerned with f of x. That can come out. Okay, there's no k there. The limit's concerned with k. It's not concerned with f of x. F of x is basically a constant in the eyes of the limit. Sounded poetic. Anyway, so here we go. We got the f of x going out, and now we have the limit of all of this. The eyes of the limit. I don't know. Never mind. Well, that's over k. Notice we still got to divide by g of x and g of x plus k. Okay? And they're dependent on the limit as well. Okay, so let's be very clear about that. So let's make sure we do the following. Okay, limit, k goes to 0. Okay, so it's going to be g of x plus k. And notice that the k's are here. The k, as I've divided each term of the numerator by it, are here and here. And of course, you know why they're there, because now I can strategically identify them, this as f prime and this as g prime, which finishes the proof. So we got g of x times, this is f prime, okay, minus f, okay, times g prime. And now, what's the limit as k goes to 0 of all this? Well, as k goes to 0, g of x plus k goes to g of x. And there's already a g of x there, so it's g of x squared, isn't it? All right, there you go. So that has been proven. We love proving math statements, from the most mundane to the most obscure. We love them all, and we are going to try to get through every single one of these. Please present questions in the form of challenges. We love tackling hard math problems. Until next time, enjoy the math.